We are talking about properties of logarithms. And the thing that I most want you to know, because it'll help you remember the properties of logarithms, since logarithms are just exponents, and we already have rules for exponents, those same rules apply to logarithms. They look a little bit different because they're written in logarithmic form, but it's the same thing. Let me, before we just look at the notes, let me ask you something about this problem I've written down. Where's my screen? There we go. What about log of 1,000? Just log of 1,000. Can you tell me what that is? What is the base understood to be if it's not written? 10. So we're looking for the exponent of 10 that gives us 1,000, and 10 to the 100 would be way too big. What is it?
Wouldn't it just be 100?
Well, let's check it. If I change that to exponential form, that would be saying 10 to the 100 equals 1,000. Is that right? Oh, heavens no. 10 to the 100 is huge. We don't even have a name for a number that big. So no, it's not 100. You don't just divide 1,000 by 10. You're looking for the exponent of 10 that gives you 1,000. That shouldn't be stumping you. Start multiplying by powers of 10 on your fingers and see how many times you have to multiply 10 by itself to get 1,000. Anybody on Zoom?
3.
Yeah, thank you. 3. And that checks, you can raise 10 to the 3rd power, and sure enough, you get 1,000. So that's just your brain waking up on a Monday morning, I suppose. But if it's any more than that, I'm concerned, because you should understand when I write log of 1,000, I'm looking for an exponent of 10 that gives me 1,000. All right. Now, we already know that, and we can check it. What if we wanted to find that answer a different way? What if we wrote log base 10 of 1,000 as log, it's still base 10, of 10 times 100? What I'm going to show you is why this property works. This property, the product rule for exponents, says if you multiply two expressions with the same base, you add their exponents. That's the property product rule for exponent. Let me try that again. That's the product rule for exponents. The product rule for logarithms says the log of a product can be written as the sum of two logs. Again, log base b of m times n is just two exponents multiplied together. If you have log base b of m, that's an exponent, plus log base b of n, that's an exponent. So it's the same thing as saying when you multiply two expressions with the same base, you add their exponents. And I can show you that it works right here. If we use the product rule on that, we'd say log of a product can be written as the sum of two logs log of a product, that's sum of two logs. Let's evaluate this and see if we get the same answer. What's log base 10 of 10? That's 1. Log base anything of itself is 1. What's log base 10 of 100? Did we get the same answer that we got doing the problem a different way? Yeah, we did. So that's just one example showing why the product rule says what it says. The log of a product is the sum of logs. And instead of memorizing this mathematical mumbo jumbo here, you need to learn to say these words to yourself. That's why I'm repeating them several times. The log of a product is the sum of the logs. All right, I'm going to show you a good example of that in the book rather than just doing one on paper, because these two examples are pretty easy. Example 1, part A says log base 4 of 7 times 5. Well, that can be written as log base 4 of 7 plus log base 4 of 5. There's really nothing else you can do with that, because I can't tell you the exponent of 4 that gives you 7, and I can't tell you the exponent of 4 that gives you 5. So we expanded that expression, but it wasn't really helpful. We just did what the directions said. The B part is log of 10x. That's a product. That's log of a product. It can be written as the sum log of 10 plus log of x. And then you can simplify that further, because log of 10 is just 1. That's just 1 plus log of x. Now, I didn't see any point in typing checkpoint 1 when it looks identical to example 1. So that's why I don't have an example of that in the notes. Example or objective 2 is the quotient rule. Let me show you something else that I just wrote down. You can tell me what log base 2 of 16 is. What's log base 2 of 16? You're looking for the exponent of 2, that gives me 16, and that exponent would be 4. I want to show you that the quotient rule for logarithms works as well. The quotient rule for exponents says when you divide two expressions with the same base, you subtract the bottom exponent from the top exponent. The quotient rule for logarithms says when you have log of a quotient, this log of a quotient is the same as that quotient. You can write it as the difference of 2 logs. The log of a quotient is the difference of the logs. If we take that same problem, this is log of a quotient, and 32 divided by 2 is 16. So we're just working this problem a different way. If we write log of a quotient is the difference of 2 logs, log base 2 of 32 minus log base 2 of 2. Let's see if we get the same answer. What's log base 2 of 32? Five. 2 to the 5th gives you 32. What's log base 2 of 2? It's 1, just like this log base 10 of 10 was 1. Log base anything of itself is 1. If we do the problem this way, do we get the same answer? Yeah, we do. So the quotient rule for logarithms works. And what, Dominic, what's making you smile? The quotient rule for logarithms, again, rather than memorizing these symbols, what you need to learn is these words. The log of a quotient is the difference of 2 logs. I'll show you a good example in the book, and then we'll go on to our third rule. Example 2, log base 7 of 19 over x can be written as, here's the difference of 2 logs, log base 7 of 19 minus log base 7 of x. And you really can't simplify either one of those, so you're through. But the B part says natural log of e cubed divided by 7. I can separate that into natural log of e cubed minus natural log of 7. And I can simplify natural log of e cubed. What's the natural log of e cubed? Natural log and E undo each other. So if you raise, if you say, what's the exponent of 3 that gives you E cubed? I said the wrong thing. What's the exponent of E that gives you E cubed? It's just 3, because natural log and E undo each other. So you could simplify that B part a little bit. And again, I didn't type checkpoint 2 because it's identical to these two with different numbers. I've typed some problems when the exercises get a little bit more difficult than the example shown in the book. All right, let's figure out one more rule. What about log base 2 of 32? Actually, you told me that right here. Log base 32 or log base 2 of 32 is 5. I want to show you that the power rule for logarithms works. And here's what the power rule for logarithms says. You know that with exponents, when you raise one power to another power, you multiply those exponents. So the power rule for, first typo, logarithms. So the power rule for logarithms says if you have log of something to a power, log base B of M is an exponent. You're raising it to another exponent. You can just multiply that second exponent by the first exponent. The first exponent was log base B of M. So the way that you need to remember that is the log of a number to a power is that power times the log. And to show you that that works, I've written this problem a different way. Log base 2 of 2 to the 5th is the same thing as log base 2 of 32. But if that third property works, I can say log base 2 of 2 to the 5th is the exponent times the log. And what is log base 2 of 2? 1. So this is 5 times 1. We get the same answer. So this was an illustration that the product rule works. This was an illustration that the quotient rule works. This was an illustration that the power rule works. Now, that is, we use properties of logarithms to expand logarithms and to condense logarithms. In calculus, sometimes we'll have the log of some horrific ugly, and I'll just call it ugly. Hey, this is log of ugly. But to take the derivative, it's easier if we can break that big ugly apart. So we'll take something, don't write this down, I'm fixing to scribble it out, but we'll take something horrendous like log of x times x plus 5 over x squared minus 7. That would be pretty bad to take the derivative of, but we'll use the properties of logs to break up this log argument, this really ugly argument, and make it easier to differentiate. That's why we take logarithms apart. And then going the other direction, sometimes we put logarithms back together when we're trying to solve an equation that has several different logs in it. We'll put the logs back together as a single log, and that'll make it easier to solve the equation. All right. Let's see what these are on page 472, 473, and then we'll work some examples. Properties for expanding logarithmic expressions. those are the three rules we just talked about. Those are the rules we'll use: the product rule, the quotient rule, and the power rule. Common blunders, this one's huge. Natural log of x plus 3. Tell me something. Let me pull up my paper again. Here's one of the most common mistakes in algebra 1. I have folks distribute the square. I have folks that tell me that's x squared plus y squared, and that is most definitely not correct. You cannot distribute an exponent through a sum. For the very same reason that this is illegal, this is illegal. You cannot distribute a log through a sum. But I see folks do that. Natural log of x plus natural log of 3, as if natural log was a number that you could distribute. If you had 5 outside parentheses and x plus 3 inside, you could distribute the 5, but that's not what natural log is. It's a function. It's log of something. So watch for that. All of these in the right-hand column are common mistakes. I have folks distribute a log through a sum. I have folks distribute a log through a difference. I have folks take the log of a product and write it as the product of 2 logs. Log of a product is a sum of 2 logs. That would have to be a plus right there. Log of a quotient, you can't just take the log of the numerator and the log of the denominator. You have to use the quotient rule. So I think it would be helpful if, before you started tonight's homework, you look at all of these things that are wrong and figure out why they're wrong. Make sure you're avoiding those common mistakes. Okay, that's all I wanted to show you before we get to some examples. Yes, ma'am.
The last one.
The last one, gotcha. Oh, yes. Yes, I'm glad you pointed that out, Chastity. This last one, log base b of m times n to the p, that exponent p only applies to the n. If you bring it out in front, then you're saying it belonged to the m and the n. If I took this right-hand side and put the p back as the exponent, it would be the exponent of the mn in parentheses, and that is not what it originally was. So yeah, that's what's wrong with this last row. All right, so let's use these properties to expand some logarithms and to condense some logarithms. Objective 4 says expand logarithmic expressions. Again, we do this in calculus, this B part. If I had to take the derivative of that, it would be much easier if I expanded the logarithm and then took the derivative of each term. That's why we're practicing this. All right. Part A, log base B of x to the 4th times cube root of y. One thing that you always want to do is write radicals as exponents so that in the last step you can bring the exponent out front. What exponent means cube root of y? 1/3. So I could rewrite this as log base b of x to the 4th y to the 1/3. I haven't used any properties of logs. I've just rewritten a radical as an exponent. And then my product rule for logs says the log of a product can be written as the sum of the logs. That's what this is, log of a product. You could put a little dot there if you wanted to show it was multiplication. The log of a product can be written as the sum of 2 logs. That was That was the product rule. Yes, sir. I have one more step. There's one more thing I can do, and I try to make that as clear as possible on the test. I believe I wrote the instructions, write radicals as exponents and write exponents as factors. What I mean by write exponents as factors is use this third rule, the power rule, that says you can bring these exponents out front. 4 log base b of x plus 1/3 log base b of y.
I didn't know.
Yeah, when we get to practicing a little bit, I'm not gonna need to write down any of that. I've done this enough to go straight from this to the answer. And once you can do that, skip the middle steps and still get the right answer, you are fine skipping the middle steps. I wrote down everything I could think of that would help anybody, but I didn't really need those 2 steps either. I can't tell you, I can't explain to you yet how easy it is to take the derivative of this, where taking the derivative of that would have been very difficult. All right, let's do the B part. Again, the directions say write radicals as exponents. So what exponent means square root? 1/2. Is it okay if we go ahead and say, break that into the difference of 2 logs? I don't think that would be skipping too much. Log base 5 of x to the 1/2 would be the first term. Then the log of a quotient is written as the difference of 2 logs. So I'd have minus log base 5 of 25y cubed. I'm not finished, but I have written the log of a quotient as the difference of 2 logs. All right. Could I bring this 3 out in front of the log now? All right, bring this 3 out front. No, because if I did, I would be saying it applied both to the 25 and the y. If that 25y was in parentheses, then I could bring the 3 out front. But as it is, that 3 doesn't apply to the 25. So there's something else I need to do before I use the power rule, and that's to recognize that 25y cubed is a product. I need to use the product rule to break that apart before I use the power rule. Again, put a little dot, helps your eyes see that, and put a little dot. Now, I'm going to make the most common mistake here. You tell me what's wrong. You've been in my class long enough to know when I say that, it's usually a parenthesis mistake, because parenthesis mistakes are, yeah, way too common. Do you see why that's wrong? I was subtracting the log of a product, so I need to be subtracting the whole difference of 2 logs. If I don't have those last 2 in parentheses, that means only the 25 was in the denominator. All right. Any questions so far? We can take one more step, but if anybody has a question, I want to answer it now. All right. What can we do in the first term? I see one thing. I can bring the 1/2 to the front. That's the power rule. Log of a number to a power is a power times log of the number. What about log base 5 of 25? Is there anything I can do with that? The answer is yes. It's just 2. The exponent of 5 that gives you 25 is 2. So distribute that negative and it'll be -2 minus, because I'm distributing the negative completely. And how can I write this last term? Three log base 5 of y. That's expanding logarithms. Any questions? All right. Before we go on to condensing logarithms, I want you to notice something. In this first answer, both of these coefficients in the A part were positive, and both the x and the y were in the numerator. I mean, I could put them over 1. I don't need to, but they're both positive. That means they both have positive exponents. And when we first learned exponents, anything about negative exponents, we learned that anything with a positive exponent is going to end up in the numerator, and anything with a negative exponent is going to end up in the denominator. The same thing is true with logarithms, only instead of saying anything with a negative exponent ends up in the denominator, you want to say anything with a negative coefficient came from the denominator. In the A part, both of these had positive coefficients and both factors were in the numerator. But here, the 2 and the 3 log base 5 of y had negative exponents. They both came from the denominator. If you get that, it makes putting logarithms back together easier. In the A part, I can see that I would put the 2 back as the exponent of the x. I'd put the 1/3 back as the exponent of the x plus 5. But because both of these coefficients are positive, would those factors be in the numerator or in the denominator? Yeah, I wouldn't even have a fraction. I would just, notice this says single log. When I put logarithms back together, I only have one logarithm, and this will be log of a product. The product will be x squared times x plus 5 to the 1/3. You really don't have to have these outer parentheses, because if you have the argument as a product, it's understood that the natural log applies to the whole product. It's not wrong if you use those outer parentheses, you just don't have to. And I think, I was wondering in the homework, if MyMathLab would take x plus 5 to the 1/3, or if it wanted you to write the answer as cube root of x plus 5. I think I tested that and it took my answer either way. So you don't have to write that back as a radical. All right, the B part, I'm seeing that the 2 can go back as the exponent of the x minus 3. And then I'll have the difference of 2 logs. Do I put the difference of 2 logs back as a product, a quotient, or something else. A quotient. The difference of two logs is put back together as the log of a quotient. And notice that log that had a positive coefficient, that factor ended up in the numerator. The log that had a negative coefficient, its argument ended up in the denominator. All right, last one of these. I can put each coefficient back as the exponent. And you may have a question about when you put this 2 back as the exponent of 5, do you put it back as 5 squared or 5 to the negative 2? Technically, you can do it either way and you'll get the same answer. It's easier for me if I just put the number back as the exponent and leave the subtraction there. I think I'll put in a middle step on this one. I'll take that step of writing each term with its coefficient back as the exponent. And it's easy for me to see when I put that back together as a single log. Tell me what's going to go in the numerator. The x to the 1/4 is going to be in the numerator. Is that all? Yeah. What's going to go in the denominator? The 5 squared, I'm going to go ahead and call it 25 just because that's simpler. What else? Y to the 10th. These two processes, expanding logarithms and condensing logarithms, are just inverses of each other. They undo each other. You could put our answer to the C part up here as a problem C under checkpoint point 4 and take that logarithm apart. This would be the answer when you did. All right. I feel like you may need some more examples of that, but the examples in the book are so good, I never want you to stop referring to those. Example 4 is taking logarithms apart. And I love how Mr. Blitzer just right out there in blue beside each step, it's telling you which property he's using in each step. The same thing, the B part's a little bit uglier. But again, those steps out to the side are what's so helpful. And then example or checkpoint 4, all the checkpoint answers are in the back of the book. And then examples of condensing logarithms, example 5, and these 2 checkpoints are in the back of the book. Hey, somebody asked me about the answers again, and I figured out why y'all were having trouble finding the answers. Some of you were in here when I said this, but I want to show those of you who weren't. When you're doing those review problems for the test, and you want to check your answers, if you just go to eText Contents, it shows you chapters P through 6 and then Appendix. When you click on Appendix, it doesn't say anything about the answers. So I see why you're having trouble finding the answers. But, and I'm going to mention that to the publisher and say, you know, you need to fix this. But if when we clicked eText Contents, we had just clicked eText that mirrors your textbook, When you open eText that mirrors your textbook and scroll all the way, well, table of contents, and scroll all the way to the bottom, then it has answers to selected exercises. You might have to click to find exactly what page the chapter 2 answers start at. But the answers to the checkpoint exercises are the first thing that's in each section. So if you're reading through examples in the book and you're doing the checkpoint exercises after each example, here are all the answers to the checkpoints. And then a few pages over, you'll see all the answers to the review and all the answers to the test. All right. We have one more thing. And it's a big, nice thing. I think I'm through showing you stuff in the book. Let's talk about this change of base property. Now, some calculators have gotten, I mean, even cheap calculators have gotten so, let me do everything for the student, that they actually have a button that you could use to enter things like log base 2 of 32. Some calculators now let you enter a base other than 10 and E. But most of us, our calculator only will do log base 10 or log base E. Which button does log base E? One of my Harriman people, which button does log base E?
LN.
The natural log button, all right? And we don't have a button that'll do log base 2. That's where the change of base property comes in handy. The change of base property lets you change log base anything to one of the 2 bases that you do have buttons for on your calculator. You can change log base B of M to log base anything else of M divided by log base anything of, okay, second cycle of the day. That's supposed to be B in the denominator. Log base A of M divided by log base A of B. And if we're going to change log base B to some other base, it would make sense to change it to a base that we have a button for on the calculator. Either change it to base 10 or base E. So we're going to do this same problem twice, once using common logarithms, that's base 10, once using natural logarithms, that's log base E, and show that you get the same answer both times. All right. If you're having trouble remembering what goes in the numerator and what goes in the denominator when you use the change of base theorem, the M is over the B in logarithmic form. The M is over the B in the change of base property. So let's rewrite log base 7 of 2,506 as base 10. According to the change of base property, that would be log base 10 of what goes in the numerator. No, the M is over the B here. The M is over the B here. So the 2,506 is what goes in numerator. I may have, because I do that sometimes. Log base 10 of 2,506 divided by log base 10 of 7. Now I want somebody to punch that on the calculator and let's say round it to 4 decimal places.
It would be 4.0220.
4.0220. 0.0220. Anybody second that? All right, Silas says you're right, Hallie. All right. Let's show that you get the same answer if you use natural logs. Enter natural log of 2,506 divided by natural log of 7 and see if you get the same thing. Do you, Brady? You don't? Oh, goodness. Miss Emma, did you get the same thing? Brady, I think you just punched something wrong. Punch it again and
I
let's
don't have a
make,
calculator with me, so I can't do this.
and that would not be easy to do in your head. Okay. So we do get the same answer whether we use log base 10 or natural log, but maybe I did both of them wrong. Maybe that's not the right answer to either problem. Well, logarithms are checkable. If I say log base 7 of 2,506 equals 4.022, what would that be in exponential form? The base is what? No, this original problem. In exponential form, the base is 7. I'm saying the exponent is 4.0220. And if I punch that on my calculator, I better get something darn close to the 2,506. Do I? Do you? Yeah, darn close to 2,506. The only reason we don't get exactly 2,506 is that this answer is rounded. So the change of base theorem works. And the most common mistake I see on the test is folks, there's one problem that has 5 or 6 parts because each part's real easy. It's something like, what is, let's say, log base 7 of 49? What's log base 7 of 49? You're not dividing, Dominic. You're saying, what's the exponent? What's the exponent? Yeah, 2. That's right. And then, what if I say log base 7 of 1/49? What's that? That's -2, because 7 to the -2 gives you 1/49. And then I'll do something sneaky like log base 7 of -49. And what will you say for that? That's undefined. Undefined because there's no exponent of 7 that gives you a negative number. You can't take the log of a negative number. And then I could do something like log base 7 of 7. What would that be? Log base anything of itself as 1. Let me give you 2 more parts. I could say, what's log base 7 of 1? 0, because anything to the 0 gives you 1. And then here's what you have to watch out for. If I say log base 7 of 40, after all the A, B, C, D, and E problems, somebody always leaves F blank because they're still trying to squint and figure out the exponent of 7 that gives you 40. I can't think of an exponent of 7 that gives you 40. That's when you have to think change of base formula. That's log of 40 over log of 7, and then punch that on the calculator. There's one, what is it? Somebody have it? There's one pretty much just like this, different numbers on the test. Don't forget that log of 0 or a negative is undefined. And logarithm that you cannot evaluate in your head, you use the change of base theorem for to get that answer. Okay, that's close. It's about, I knew it was close to 2 because 7 squared is 49. That's a little too big. So it's something just a little bit smaller than 2. All right. We have, almost never happens. There's 2 things I'm thinking. Yes, ma'am.
So for parts that you do, where it's undefined, would you ever be looking for 2i or not do that because it's so I know you can't have the negative base.
That's not, the log of a negative is not the same as the square root of a negative. An I wouldn't fix it. Yeah, that's just undefined. All right. I don't want to waste this 2 minutes or this 10 minutes. I said before some of you came in that if we finished early, we were going to do just a few minutes of head start on the next section, so that if we finish early Wednesday, maybe we'd have a little bit of time left over for you to ask questions. I don't know if that's going to happen or not. Be prepared just to ask me your questions via email, or I'll hop on Zoom with you if I need to. But there is one other thing I want to show you. And then we'll see if we have time to do anything from the next section. I don't really think so, but this is so valuable that I don't want you to miss it. Could show you, if I could show you on my phone. Yeah, that shows up pretty good. I think it was last Friday, I sent all of you a link to something in Quizlet. Quizlet is a fantastic app. I asked Brady if he had ever used it before, and he said, been using it since the 5th grade. So y'all may be much more familiar with it than I am. But I sent you this message, and here's how cool it is. You don't have to download anything. If you go straight to Quizlet using that link that I sent you, this is not helpful. This is matching, I believe, and you don't need to do that. But if you just close that and then scroll down to flashcards, flashcards will help you. So everybody in Harriman, unmute. I want everybody to hop in here and give me some answers. This particular stack is for rational functions, because Brady and I were talking about rational functions and how do you find the x-intercept? How do you find the horizontal asymptote? And I found this stack on Quizlet already made, and I'm going to find more good stacks and put them in there for you. But tell me how you find the hole in the graph, hole in a graph. Anybody? If you cancel a common factor, then the factor you canceled out gives you a hole in the graph, and that's exactly what that says. When a common factor is divided out of both the numerator and denominator, that's when you're going to get a hole in the graph. Yes, sir. It's yes, and actually that's a different flashcard. This first flashcard just said, when are you going to get a hole in the graph? And then there's another one that says, how do you find the hole in the graph? But Dominic here said, if x minus 1 is the factor you cancel out, you set x minus 1 equal to 0, and that's how you get the hole in the graph at 1. and then you put 1 back into the simplified version, that gives you the y. Yes,
So is there ever gonna be, the whole is just a point, is there ever gonna be like one space that's like
there, the best I can answer that, Chastity, is if you ask me to graph log of x minus 3, remind me what the graph of a logarithm looks like. What's its critical point? Critical point is normally 1, 0. For the exponential function, it's 0, 1. Logarithmic is 1, 0. Only this has been shifted 3 to the right. So its critical point is 4, 0. And logarithms have a vertical asymptote, x equals 0 normally, but this has been shifted 3 to the right. So the vertical asymptote's x equals 3. So what I wanted to show you in answer to your question, Chastity, when you're talking about, is there a whole space that's a whole? Well, really, you could consider this whole space as a whole, because you can't let x be anything less than 3, or you're taking the log of a negative number. So I'm going to say no. You don't think of a whole space as being a whole. What a whole represents is something that's not in the domain of the function. And here, everything to the left of 3 is not in the domain of the function. That was a good thought. All right. Yeah, we're not going to have time to do anything in the next section. So let's look at a couple of those. Ooh, this one's good. If the power of the numerator is greater than the power of the denominator, what's the horizontal asymptote? Top of the fraction's getting bigger faster than the bottom of the fraction. What are you saying, Dominic? Actually, I asked what's the horizontal asymptote, and the answer's, oops, dang it. Dang it, dang it.
which one was it?
If I had tapped instead of swiped, Dominic, it would have said there is no horizontal asymptote, because that's what the question was about. What's the horizontal asymptote? When there's another one, Dominic, that says, when is there a slant asymptote? Not just any, like x cubed over x wouldn't give you a slant asymptote. Oh, when the power of the numerator is just 1 more than the power of the denominator. All right, so there are some really good questions in here. The only thing that you may have trouble with, certainly the ones that just have word questions, you should be able to snap right through those. The ones that you may stall out just a little bit is ones that say something like, what's the domain? And you have to factor to find it. If you're letting the game pace itself, you may not have time to factor that real quickly in your head, but just pause it and make sure you can find the domain. I think this stack would help you a lot with making sure you know how to find everything you have to find for rational functions. So use that, and as I find other good stacks that would help you, I'll put them in there and send you a link to them. All righty, that's it. Y'all have a great day. Keep working on that practice test and email me any questions you have. I'll be happy to help.
Don't forget that some of us have a test.
Oh, yes, tomorrow. Oh, I'm so glad you said that, Emma. Tomorrow, some of you have the ACT. We have to have class. We can't just cancel class for a day, but I will get the video on YouTube as quickly after class as I can. By the time you get out of the ACT, I should have that video up there for you. So there won't be many of us tomorrow, but I'll see you. All right, have a great day.
Can you hear me?
Yes, sir.